So this is a video regarding the topic term by term integration of Fourier series. So in the previous video I was discussing about the term by term differentiation of Fourier series, and I can say that this is easier than this term by term differentiation of Fourier series, and how I will explain in this video. So before starting the term by term integration, I will remind you regarding the previous discussion that where we were discussing about the term by term differentiation. So see, there was a condition that the function, the periodic function of which we were interested in term by term differentiation, that function has to be continuous in this defining interval. Suppose this is the function fx mod of x in the defining interval minus pi to pi. So in that interval function should be continuous, and after this periodic extension also it should be continuous. Okay, so that condition was satisfied by this function, but same was not uh, same was not happening for the function fx is equal to x. So if you do the periodic extension of this function, there we saw some discontinuity. Okay, so this type of function cannot be term by term differentiated. So again I will say that the function which are continuous in defining interval, and the function which will be continuous still after the periodic extension, those type of function can be only differentiated term by term to obtain a Fourier series after differentiation also. Okay, so in case of term by term integration of Fourier series, this type of condition we need not to follow. Only thing is that the function which we are interested has to be, suppose fx is the function, has to be piecewise smooth. That was also one condition in earlier case, but here only piecewise smoothness of a function or periodic function can satisfy all the conditions for its term by term integration. So function has to be piecewise smooth. Okay, there can be discontinuity, there can be jump type of discontinuity that will not affect on this term by term integration. Why? Because if you see uh, suppose uh, I'll draw one function like this. Okay, so in this function is defined from minus pi to pi. So this is the fx plot. So in this function there are three discontinuities, 1 2 3. So here we cannot do this function, or we cannot do the term by term differentiation for this function, because though this function is piecewise smooth, this number of or any presence of discontinuity does not allow to do the term by term differentiation. But if you do the integration of this function, how the integration plot will be look like? So we have to do integration. Okay, suppose we are doing the integration from x. So if you do the integration we know it gives the area under that curve. This area will increase. Okay, after that it will increase. Okay, like this. So if you see the area plot, that integration of fx, this area plot, it is continuous. Okay, though this function was discontinuous, the area plot will be continuous because area will increase, is not it? So there is not occurring any discontinuity. So any smooth function, piecewise smooth function, will have a continuous function after integration, and because of that there is no any problem of having a Fourier series after term by term integration of a function. Okay, so and that is the thing. But interestingly, We will not always have a Fourier series after term by term integration. How that thing we'll discuss here. Okay, we can do term by term integration of a piecewise smooth function or a function which is having Fourier series, but after integration it is not necessarily will get a Fourier series always. It can be Fourier series or it cannot be Fourier series after integration. Okay, so we'll write down the theorem first. After that we'll uh, discuss this thing. Theorem: the Fourier series of any piecewise smooth function fx can be integrated term by term, and the resultant series will be a infinite series. Not necessarily Fourier series. Okay, it is not necessary that after integration you will have always a Fourier series. That thing I have written, Fourier series, and the resultant series will be a infinite series. Moreover, the infinite series converges to the integral of fx. Okay, so in the defining interval, say minus pi to pi. Okay, so that can be also from minus L to L, arbitrary variable. So here we are, all the things here we are talking in terms of the angle variable. Okay, so now what has been told that we can do term by term integration and there is no any restriction, unlike the case of term by term differentiation. But after that it is not necessary that we will have a always a Fourier series. We may have Fourier series, we may not have Fourier series. That thing I will show you. Okay, so so suppose fx is a piecewise smooth function, and we are, since it is a piecewise smooth and it is a periodic, will have a Fourier series. That thing we know already, 1 to infinity an cos nx plus 1 to infinity bn sin nx. Okay, so now we'll do the integration in the both side from minus pi to x. Here this function is was defining the interval minus pi to pi. So we'll do the integration with this limit. See, sometime here our interval is defining from minus pi to pi, therefore we are taking the integration limit from minus pi to x, and here we should take x, otherwise we will not having a function. Okay, otherwise x will be not there. Okay, so in some places you can find like this also. The function is defined with another variable, dummy variable. So after that they write like this, from minus pi to x dt. Okay, so that way also this is done. So here we are not using that another variable, we are simply using that, keeping the x same. So that is the thing. So now dx, so you have to do the integration in the right hand side also. A naught by 2 dx integration, sorry, minus pi to x minus pi to x summation 1 to infinity an cos nx dx summation integration before that minus pi to x 1 to infinity bn sin nx dx. Okay, so in the right hand side after integration we will get a naught by 2x plus a naught by 2 pi plus inside the summation we will take the integration. After that we'll have an cos, it will become sin nx divided by n, limit will be x minus pi plus, so here also 1 to infinity minus bn, because integration of sin nx minus cos nx divided by n, then cos nx limit x to minus pi. Okay, so after that a naught by 2x plus, this thing will writing same. After that we'll arrange the thing, you will see. Okay, so summation 1 to infinity it will become an divided by n sin nx, because we know this second limit will become, it will become 0, sin n pi it will become 0, therefore not required to put that limit, plus here we can take this negative sign outside of the summation. Okay, so bn n cos nx minus cos n pi, because cos minus pi is equal to cos pi, so that negative sign will be not there due to that property. Okay, so after that we can arrange this thing, a naught by 2x plus a naught by 2 pi plus an divided by n sin nx, okay, minus bn divided by n cos nx plus bn divided by n minus 1 to the power n, because we know cos n pi is equal to minus 1 to the power n. Okay, so now after that we'll obtain we'll write this thing, these components again. So this term and this term, if you see there is no any cosine components here, there these are DC components, we can write together. Okay, a naught by 2 pi plus summation bn n minus 1 to the power n, n from 1 to infinity. Okay, so these terms we have written together, then plus minus we are taking inside the summation bn divided by n cos nx I hope you are understanding what I am trying to do here, I am going to rearrange this thing to in the form of a standard Fourier series expression. Okay, an divided by n. Okay, okay, so this thing we have obtained. So see here, it was fx dx minus pi to pi. Here if you see, as mentioned in the theorem, this term is coming, this is a linear term. Okay, so definitely in right hand side, this whole series, it is an infinite series and it is a converging series, but it is not a Fourier series because of this term. Okay, so if you want to make this Fourier series, then we have to take this term, this linear term, into the left hand side like this. If we arrange fx dx minus a naught by 2x. Okay, so in place of this we can write that bigger, with bigger a naught 2, means in whole thing we are representing as a naught by 2 because we are going to arrange this thing in terms of a Fourier series, that is standard Fourier series. So summation n from in 1 to infinity, it will become uh, an, okay, cos nx plus summation bn sin nx. Okay, so now if you see, we have obtained some new relation or new relations for these coefficients, new coefficients, that those are a naught. A naught, what is the value of a naught? A naught, small a naught by 2 plus summation 1 to infinity bn minus 1 to the power n, then an is equal minus bn divided by n, and bn is equal an divided by n. Okay, so this is the if you see, this is the this expression, this is the new expression for Fourier series. Okay, but this expression is giving the Fourier series for this function, not only of that integral function. We have to take this linear term to the left hand side. Okay, so in some examples you may not find this a naught by 2, means some examples a naught by 2 maybe not there. For example, if you are talking about a odd function means only sine series will be there, so there this a naught by 2 term will be not there. Okay, so here this expression has been found only for general uh, Fourier series. Okay, so we'll do one example now, and now uh, and this will be clear to you. I hope this, up to this, it is clear to you that why we have to take this linear component to the left hand side, and to represent, means now we can represent the Fourier series of this function. Okay, so now we'll take one example, simplest example that I frequently use that example. Like if you have been given the Fourier series of x, that is odd function, minus pi to pi. Okay, and we know the Fourier series of x, that is summation 1 to infinity 2 minus 1 to the power n plus 1 divided by n. Since it is a odd function, only there is sine series will be there. There is no any a naught and an. Okay, so now you have been asked, find the Fourier series of x square. Knowing the Fourier series of fx equal to x, find the Fourier series of x square. Okay, like in earlier case where term by term differentiation we were knowing the Fourier series of x square, we were asked to find the Fourier series of x. Oppositely here, knowing the Fourier series of fx, we are fx equal to x, we have been asked to find the Fourier series of x square. So seeing the problem, we can say that definitely if you do the integration of x, that x square term will come. So you do the integration, and integration has to be done from minus pi to x. You always see this minus pi here, okay? Then x dx, then it will be summation n to infinity minus pi to x 2 minus n plus 1 divided by n sin nx, okay? Then dx. So now if you do the integration, in the left hand side it will become x square by 2 minus pi square by 2. So in the right hand side, if you take the integration inside the summation, it will become 2 minus 1. Here if you do the integration of sin nx, another minus 1 will come, so it will become n plus 2. So in place of n plus 2, we can simply put n, okay? So it will become cos nx, then x minus pi. After that, 1 infinity 2 minus 1 to the power n, n here it should be n square, because in denominator another n will come, okay? Then cos nx, after putting the limit, cos nx minus cos n pi. So in place of cos n pi, we can put minus 1 to the power n, because we know cos n pi is equal to minus 1 to the power n, okay? After that, x square by 2 minus pi square by 2, integration summation 1 to infinity 2 minus 1 to the power n square. So it will become cos nx, okay? Then cos nx, then okay, then summation n to infinity 2 n square. This minus 1 to the power n minus 1 to the power n, if you multiply, it will become minus 1 to the power twice n, that is equal to 1, because irrespective of the value of n, even or odd, it will become always even, twice n, okay? Because minus 1 to the power twice n will be 1. So after that, we will obtain x square by 2 minus pi square by 2 is equal summation 2 minus 1 to the power n square cos nx 2. We know that the summation of 1 by n square is pi square by 6, okay? This thing we already know. I will also make one video to find how we can obtain this value, but this is known value, pi square by 6. Then we can write this thing, pi square by 6. If you put pi square by 6, we will obtain pi square by 3 there, okay? So after that, now since we have been asked to find the Fourier series of x square, so we are making this thing as a subject, okay? So we are taking pi square by 2 inside the bracket, inside to the right hand side. Now if we take this to right hand side, after that we will obtain 6 pi square plus 2 minus 1 to the power n square cos nx, okay? Okay, now if you multiply both sides with 2, then it will obtain pi square divided by 3 into 4 minus 1 to the power n square cos nx. Okay, so this is the Fourier series of x squared. That thing we already know. So in this problem, because a naught was not there, and therefore the we cannot directly correlate this Fourier expression in the standard one that we did earlier. But thing is that you have to rearrange after integration. You have to rearrange the expression such a way that you can make the x function uh, as the subject. Okay, that way you can find the Fourier series. And always remember, in the Fourier expression there cannot be any term which is multiplied by x, okay, or any x square quadratic term. So Fourier series can be only can have a DC component, can have sine component, cosine component together, or can have either sine component or cosine component. That is the thing. So we have seen that we can integrate a Fourier series of a piecewise smooth function. No such specific conditions are there, like in the case of term by term differentiation of Fourier series. So we have to only rearrange the expression after the integration. Okay, so if you are having any problem, or you can ask me in the comment section, and in the later video I will make one video on this thing, how we can obtain, how the summation of 1 by n square can be pi square by 6, that thing. Okay, so thank you very much.